Welcome to another podcast. In this episode, we're going to be taking a look at a topic called probability density functions. This is sort of our first step at discovering the relationships between calculus and probability. Now, you're probably all familiar with the idea of probability, but probably, and I'm using the word probably a lot at this point, it's not likely that you know exactly how it's related to calculus. And the bridge between functions, probability, and calculus is something called the probability density function, or PDF for short. So if you ever hear me talk about a PDF, I'm probably talking about a probability density function if we're in the discussion of probability. So let's just talk about a quick definition of this, because with the definition comes a couple of talking points here for us, and that is a function f of x defined on the interval from a to b is a PDF provided that it satisfies two things. The first thing that has to be satisfied is the function has to be greater than or equal to 0 on the interval. In other words, if this function is going to define probabilities for us, we don't have negative probabilities of events occurring. And so the function would need to be either 0 or greater than 0 everywhere on the interval that we're concerned with. The second thing, and this is the biggest characteristic of a PDF, is that when you try to integrate the function, you get back 1. Now, in both cases here, I'm allowing for a to be negative infinity, and I'm also allowing for b to be positive infinity. So this could be an infinite interval, in which case this might be improper. So this might be an improper integral. But the point is, the area under the curve, the area under the integral here, the area under the function f of x, if it's a probability density function, is equal to 1. So why is this important? Well, if you have a probability density function, then if I talk about, so capital X here is some continuous random variable. Now, you may not be familiar with continuous random variables. Let me just give you a small explanation of what those are. It's any variable which can take on a value in some interval. For example, if I was measuring people's heights, then x would be the variable that tells me what the height is, and the interval over which it could pick a value could be anything from, let's say, 5 foot to 7 foot, or 4 foot to 7 foot, depending on the population that we're looking at. And so the point is, the variable represents any possible outcome from a continuous interval. Usually we associate these with some sort of experiment or some sort of sampling technique, but the idea is it's a variable which represents all possibilities from a continuous interval. Now, what if I wanted to ask what is the probability that the values it gives me are somewhere between two values, let's say C and D? In other words, what is the probability I choose someone with a height between 5'1" and 5'5"? Well, that depends on who's in my sample, but the point is, if I can tell you that f of x is the PDF that is associated with the continuous random variable x, in other words, if our experiment x represents heights and the function f of x tells me the probability density of those heights. In other words, is a person having height 5'5" more likely than a person having height 5'1"? Well, it would depend on the population, but let's suppose that the function told me that. Then the idea is all I would have to do in order to calculate the probability between C and D is to calculate the integral, in this case, from, let's say, C to D of the function f of x dx. and that would be a value less than or equal to 1 depending on what my intervals are. That would then give me the probability. Notice another thing that this does is, what if I ask the probability of choosing someone with a specific height, let's say x equal to c, then this would be the integral from c to c of f of x dx, which we know the integral from any point to itself is 0 if I'm integrating over with 0 interval. That basically says that if you were looking at the heights of everyone on the planet, the probability of getting someone with one specific height is basically 0. And that sort of jives with our understanding of probability. It's very unlikely that you pick a single number randomly out of an interval that matches what you're looking for, considering there are an infinite number of values on any interval. So this is all well and good, but it's sort of hard to understand what a probability density function is without a couple of examples. And luckily for us, there are 3 standard examples of probability density functions, which makes this much more clear. So we're going to start with the most basic probability density function that you can come up with, and that's something called the uniform probability density, or the uniform density function. And the uniform density function is basically, let's let everything have the same probability of occurring. So I'm going to call my density function f of x equal to k, in which case if I wanted to define the probability of the random variable being between a and b, if we have a uniform density, I'm telling you that's the integral from a to b of k dx, which when you integrate is k times b minus a. Now, that may not seem like a big deal that we're able to find that probability, because you probably can't see the picture in your head. The picture makes this a lot better. So the idea here, picture-wise, is that I'm looking at some event occurring, and I want to know the likelihood that it occurs between A and B. Then, in order for this to have a height of 1, you see here that k has to be equal to 1 over b minus a in order that this thing is going to be equal to 1 and be a PDF. That means the probability density function is always a constant valued function that leads to the area in between the interval being 1. All that says is that all outcomes of x are equally likely. Now, on a continuous interval, it's hard to come up with examples for that, but you know an example right away of where things are equally likely. For example, what if you were to roll a dice? There's only 6 outcomes. Each of them is equally likely to occur. In the case of an interval, one easy example to show you equally likely is, let's pick numbers at random from the interval from 0 to 5. Well, every number would have the same chance of being selected. So if I'm randomly choosing values from a closed interval, then the uniform density function is the PDF that describes that. All right, let's look at another one. So next up, I want to look at something called the exponential density function. So the exponential density function is given by the PDF ae to the negative ax, and this is where a is greater than 0. So a could be a lot of different values here. Let's look at a sort of a graphical example of this. If a starts out really big, then the rate of decay is going to be really fast. So if a starts really big, it's going to decay really fast to 0 at that point. So this is for a large. But if a is really small, then the rate of decay is not very fast, and so it might be something like this. So depending on the value of a, you get different pictures, but the point is the area underneath these pictures, say for example the area under here and the area under here, at least on the interval from 0 to infinity, the areas under each of these is going to be equal to 1. Now, in order to show that, I need to look at the integral from 0 to infinity of this function and show that that is indeed 1. What we immediately notice and what we predicted is we're going to get some improper integrals. This turns out to be one of them. So if you recall how to evaluate an improper integral, we're going to take the limit as n goes to infinity of the definite integral from 0 to n. If we do the antiderivative here, we're looking once again at the limit as n goes to infinity of negative e minus ax from 0 to n. And now we're almost ready to take the limit. So we're going to evaluate this at 0. We're going to get plus minus a negative plus e to the 0. And the point is, looking at this limit, the limit of this first piece, because a is greater than 0, the limit of this first piece is 0. E to the 0 is equal to 1, so the PDF, for any value of a greater than 0, this forms a PDF. Now the question is, how is this one going to be useful? So the idea is this PDF could measure failure times. That's just one example. What I mean by failure time is, let's look at the first graph that I drew here. You might have a certain component of a manufacturing process, a certain part, where most of them fail within the first 2 hours. So the largest chunk is within the first 2 hours, and then it becomes increasingly less likely that something fails out at, let's say, 5 hours. And it becomes almost impossible to find one that's still working out at 10, 12, 15, 20 hours. And so this could measure the failure rate. It could also measure survival rates. It could measure populations. You could look at a lot of different things where you're looking at the probability of something in that group persisting past a certain point. And so that's a really popular sort of application of an exponential density function. Now, there is one more that I want to look at. I'm going to need to create a little bit more room to do that, so let me just get rid of this piece that I have over here. And the last one that I want to look at is something called the normal density function or the normal distribution function. So, this is by far the most important. And the reason it's the most important is it has the most real-life uses. The function is also, unfortunately, the most difficult to talk about of the three. But let me go ahead and write it in. The probability density function for a normal distribution is given by this function. And let me write it all down, and then I'll explain the different components of it. It is a exponential. Typically, because it is squared, you see how the power x is squared here. It's typically called a Gaussian. So the name of this function is a Gaussian. And a couple of points here. The value sigma is called the standard deviation of the distribution. It measures how spread out the values of the function are, or the values of the random variable are. And then mu measures the mean of the distribution. Now we're going to talk more about the mean in a future video, or the expected value in a future video. But what does this particular distribution look like? How does it compare to the others? Well, you notice in the case of the exponential, it kind of follows an exponential curve. Uniform is constant. It turns out that the normal distribution is this nice, well, somewhat nice, this nice looking bell-shaped curve. Its center is at the value mu, which is the mean. So it is symmetric about the mean. And then if you add the standard deviation and subtract the standard deviation from the mean, it intersects the curve at its inflection points. So these turn out to be the inflection points for this curve. The mean turns out to be the max of the curve as well. So a maximum occurs at the mean. What is this saying? Well, this curve describes anything where most people score near the average, and then as you get further away, you're less likely to get a score there. So it perfectly describes things we use in education all the time because it describes testing really well. Most people score near the average of whatever the test is that you're giving, and it's less likely for a person to score really high or really low. The point is, if I was to take the integral from minus infinity to infinity of this particular function where I had a specific standard deviation and mean in mind, then the result of this would be that there is an area of 1 underneath this curve. Now, this curve is always from negative infinity out to infinity. That's how we typically think of the normal distribution. It continues on forever. It's just that once you get too far away from the middle, you're very unlikely to find anything to occur. Other areas where this is used, it's used in quality control testing. In other words, most things, like if you're taking a measurement of something, that's important for manufacturing processes. Most of the measurements will fall near the average, and then if you measure the same thing over and over and over again, you can't be perfectly precise, and so some things will be higher than the average, some things will be lower than the average, and the chance that you measure really far above the average is very unlikely, or really far below the average is very unlikely if you're measuring the same thing over and over again. So this is important for quality control because you want to sort of have an interval over which you trust your measurements. It's also important for standardized testing. And one of the most important things that it's used for is if you look at the distribution of what are called sample means. Now, let me describe what I mean by that. Let's suppose that you're picking values at random from an interval, and you take the average of those values. If you do that over and over and over again, you'll get different averages because you'll be picking different numbers. But the point is, those means, those averages, sort of line up in a normal distribution. That is far from being obvious that that's true. It's actually one of the most important results in all of mathematics. It's something called the central limit theorem. Now, we're not going to talk about that in this course, but that is an integral part of your studies of the field of statistics. And those of you that are in engineering or physics, you'd be surprised at how important this result is to the work you do on a daily basis in those fields. And so you'll talk about something called the central limit theorem, but it basically just says that if you take the average of a sample over and over and over again, that those numbers themselves wind up being normally distributed, and so they obey this normal distribution function. So if you've ever heard of the bell curve, that's what we're talking about here as well, that the normal density function is the same as the bell curve. All right, this is just 3 examples of popular density functions. There are countless more examples. Just remember that something is a probability density function if it's associated with a continuous random variable. It's positive over the interval, and if you integrate it over the interval, you get a value of 1. All right, thank you for watching.